Welcome to a lesson on determining the antiderivative of a vectored valued function. This is also called indefinite integration of a vectored valued function. Notice to perform indefinite integration of a vectored valued function, we integrate each component of the vectored valued function. It's important to remember that the antiderivative of a vectored valued function is a family of vectored valued functions such that if big R of t is the antiderivative, then the derivative of big R of t is equal to little r of t. And in some cases, we are given an initial condition, and in this case, we can find the exact antiderivative vectored valued function. We'll take a look at this case in the next video. Let's take a look at our first example. And again, in order to find this indefinite integral, we want to integrate each component, which means we'll have the indefinite integral of 5 divided by t squared, which we'll write as 5t to the power of negative 2 dt times I, and then we'll have minus the integral of 4 square root t, which we'll write as 4t to the power of 1/2 dt times j. And now we'll apply the power rule of integration to find our indefinite integrals. So we're going to add 1 to the exponent and then divide by the new exponent. So we'll have 5 times t to the power of negative 2 plus 1 is negative 1, divided by negative 1, plus a constant of integration, which we'll call c sub 1, times I, minus 4 times t to the power of 1/2 plus 1, that's t to the 3/2, divided by 3/2, which is the same as multiplying by the reciprocal, or multiplying by 2/3, plus c sub 2 times j. Now let's go ahead and clean this up. Notice how we have 5 divided by negative 1, that's negative 5 t to the negative 1, or negative 5 divided by t, plus c sub 1 times I, minus, here nothing simplifies, so we have 8/3 t to the 3/2 plus c sub 2 times j. So this is the antiderivative, but notice how c sub 1 and c sub 2 result in a constant vector where the I component is c sub 1 and the j component would be negative c sub 2 because of the minus. So this can be written a different way. If we let vector c, a constant vector, be equal to c sub 1i, and then it would be minus c sub 2j, we can give the antiderivative as negative 5 divided by t I minus 8/3 t to the 3/2 plus our constant vector c. Let's take a look at a second example. Notice in this case our vectored valued function has 3 components, so now we'll have 3 indefinite integrals. Let's write the first indefinite integral as 2 times the integral of 1 divided by t dt times I minus the integral of sine t dt j, and then we'll have plus the integral of secant squared 2t dt k. Well, the integral of 1 divided by t with respect to t would be natural log t. So here we have 2 natural log t plus c sub 1 I. The integral of sine t is negative cosine t. So because of this minus, we'll have plus cosine t plus c sub 2j. And now for this last integral, we'll have to perform u substitution, where the inner function 2t will be u. So if u is equal to 2t, differential u is equal to 2 dt, dividing both sides by 2. Notice how dt is equal to 1/2 du. So if we wrote this in terms of u, we would have 1/2 the integral of secant squared u du. And since the integral of secant squared u is equal to tangent u, we'll have plus 1/2 tangent instead of u to t plus c sub 3 times k. So now we do have our antiderivative, or the indefinite integral, but because of the c sub 1, c sub 2, and c sub 3, we can let vector c, a constant vector, be equal to c sub 1i plus c sub 2j plus c sub 3k. So now we can write this as 2 natural log t I plus cosine tj plus 1/2 tangent 2t k plus our constant vector c. That'll do it for this lesson. In the next lesson, we'll talk about how we can do these types of problems when we're given an initial condition and therefore find the exact antiderivative function. I hope you found this helpful.